Thank you so much for joining session 3 on wireless and mobile networks. I'm Lily Chiu from UT Austin. We have 4 very exciting papers in this session. We'll first play a video for each talk. While playing the video, we would like to invite you all to submit your question on the Slack channel. During Q&A, we'll try to cover as many questions from the Slack channel as possible. As Deepak introduced in his topic preview, this session will cover wireless and mobile networks for personal device, home, city, and all the way to satellites. The first talk will be on home network. The presenter is Ivan Ilazar. He's a 6-year PhD student candidate at Yale University. He is currently on the job market. He received his bachelor degree in telecommunication engineering at the Central America Technological University in Honduras. His current research focuses on wireless communication, programmable radio environments, and Internet of Things. Now please play the video.
Hi, everyone. It's an honor to be here to present our recent work, LAVA, Fine-Grained Indoor Wireless Coverage for Small IoT Devices. My name is Ivan, a PhD student at Yale University, and this work is a joint collaboration with my colleague, William Sussman, my advisor, Wonjin Hu at Yale University, and Jeremy Gumason at the University of Massachusetts Amherst, and Kyle Jamieson at Princeton University. According to a recent study, it is estimated that around 75 billion wireless IoT devices will be deployed by 2025. Endpoints used to be primarily near the human user, for example, laptops, phones, and smartwatches, roughly in the same 2D plane as the user. But now the endpoints can be about anywhere, for example, smart bulbs, plugs, and cameras. Endpoints can be near the ceiling, near the floor, and anywhere in between. Therefore, they can no longer be considered to be in the same 2D plane as the users, but rather in a 3D signal space. This leads to non-uniform wireless 3D coverage. At different vertical offsets from where the typical user is, antenna beam misalignment and obstacles exacerbate the non-uniformity of signal coverage. What's more, some devices use, for example, Wi-Fi, whereas others use Z-Wave, Zigbee, and Bluetooth. That is, devices with diverse performance capabilities and standards share the same environment. To recap, the fundamental problem is uncontrolled signal propagation indoors, resulting in complex, non-uniform 3D coverage. To provision high-quality coverage indoors, we need to address 2 challenges. First, protocol agnosticism. We need to improve communication between 2 endpoints, regardless of the specific wireless protocol provisions they implement. Second, decoupling from transmit or receive from the transmit and receive endpoints. That is, signal improvement needs to occur without modification to the endpoint operations themselves. This points towards modifications along the propagation path between the endpoints. Decoupling also implies no endpoint coordination. That is, we want to avoid getting any kind of channel information from the endpoints. So our solution is LAVA, a large array of vanilla amplifiers. LAVA is a mesh of multi-hop amplify and forward elements that are placed along the propagation path between 2 endpoints. It is able to handle these challenges in the following ways. First, LAVA remains protocol agnostic by relying exclusively on signal level operations. It boosts passing signals via successive amplifying forward. To remain decoupled from the endpoints, it is a separate infrastructure. That is, the mesh is not connected to the endpoints in any way, but it is able to handle the signals along the propagation path between the endpoints. To avoid coordination with the endpoints, LAVA adopts power sensing to infer active transmissions without information from the endpoints. Now, let's take a look at the LAVA design. As I mentioned, LAVA is a mesh of devices, which we call elements. Let us start with the minimalist amplifier and forward design, which we call a simple element. It consists simply of a fixed gain amplifier between a directional input antenna and an directional output antenna. This design is unidirectional since the amplifiers can only amplify in one direction. But we would like to amplify signals from and towards multiple directions. To do so, we use RF switches to integrate multiple directions into a single element. So instead of just having one antenna, we have 4 directional input antennas, and the first RF switch selects which one to use. The second RF switch allows us to select one of 4 fixed gain amplifiers, each of which is in turn connected to a different output antenna. Finally, by positioning the directional antennas towards different cardinal points, we can choose which direction to receive a signal from and which direction to send it to. For example, input north and output east. The final result, this final design is what we call the multidirectional lava element. Now, each element, because its amplifier has fixed gain, has limited coverage as well. So we need a mesh of elements. The elements need to be organized into a suitable topology to extend the coverage area. When constructing the lava mesh, there are 2 main considerations. The first one is the layout of the topology. The topology layout depends on the element design. So we can have a complex multi-directional element design, but a simple grid topology, as shown in this schematic, and as built in this example testbed that we deployed on a ceiling. Or we can have a simple element design, but a complex topology, like the hexagonal one shown in this floor deployment. The second consideration when constructing the lava mesh is the space that we leave between the elements. That is the inter-element or inter-hop spacing. The optimal inter-hop spacing is where the signal amplification at each hop compensates for the path loss from the previous hop. Note also that a fixed gain amplifier also fixes the lava mesh topology and inter-element spacing, thus simplifying much of the construction of the lava mesh. With the mesh topology, we then employ multi-hop amplifier and forward to provide coverage around the lava mesh and signal flow in any direction. Due to practical constraints, we deploy a planar testbed extended over a large area to provide horizontal coverage. Note that a dense topology will maintain good coverage between hops as well. Finally, vertical coverage is provided simply by the vertical beam width of the directional antennas that we employ. Next, we explore how to control this mesh of amplifier and forward elements. There are 3 main steps in actuating the lava mesh. First one is endpoint independent link detection. We detect the presence of an active transmission via per element power sensing and a centralized inference of active links. Second is route computation. Multi-hop amplifier and forward route between the elements closest to the endpoints is enabled. Route computation simply boils down to identifying the shortest route between the 2 elements closest to the endpoints. Finally, we need to select the state for each of the elements. Because the elements are built with fixed gain amplifiers, Lava adopts simple on-off switching of these amplifiers and selection of their input and output antennas. Now let's look at a few more details. Each element is equipped with a power meter that listens for active sessions between endpoints. Part of the signal received by the element is fed into this meter, and its power is measured. Its power is measured. So each element collects power measurements that are indicative active transmissions and sends them to a central controller. So when the first endpoint transmits, the elements that detect the signal report power measurements to the controller. The controller ranks these measurements and identifies the element closer to the first endpoint. When the roles of the endpoints are reversed and endpoint B transmits, the process repeats and the element closest to the other endpoint is identified. Note that the Lava topology serves dual purposes. It ensures coverage for both link sensing and signal amplification. After identifying the two elements closest to the endpoints, route computation is straightforward. Lava simply determines the shortest route between them. The controller then maps this route to active input and output antennas and amplifiers on the pertinent elements, and a multi-hop amplifying forward path between the endpoints is enabled. Now let us take a look at how Lava performs in practice. We run experiments using a broad range of devices to cover the spectrum of device capabilities and wireless protocols. We run experiments in an office space area that encompasses 3 rooms and a corridor. For the following results, one endpoint is placed on the ceiling, and the other at various locations and different vertical offsets from the ceiling. The devices are placed at 40 locations, and the colors indicate different transmitter-receiver pairings. The endpoint locations in this figure is only for the subsequent result figures that I will show briefly. Since Lava is protocol agnostic, it provides substantial gains for both Wi-Fi and ZigBee. In the case of Wi-Fi, the median SNR gain is 11 dB. Lava also increases ZigBee, the ZigBee RSSI, and the median gain is about 6 dB. This shows that the protocol-independent improved coverage across different vertical offsets for multiple standards that Lava provides. There are many more results in the paper. Please refer to the paper for more detailed results. We discussed several other design issues, including 3D multi-hopping dynamics and link detection, false positives and false negatives, among other things. We also present many more performance results, including throughput enhancement, mobility, power offloading, and concurrent link handling. So to conclude this presentation, we discussed how unplanned deployments lead to the lack of uniform coverage in 3D environments. Lava addresses these issues by multi-hop amplifying forward and power sensing to provide fine-grained protocol-agnostic indoor 3D coverage that is decoupled from the endpoints themselves. Finally, Lava delivers performance gains for diverse standards, devices, and scenarios. Thank you, and now I'll be glad to take any questions. Thank you.
Much, Ivan. Thank you for the great talk, and it's nice to see that Lava can support different wireless protocols. I will start with a few questions and would like to invite everyone else to submit your question on the Slack channel. So first question is, what process would you recommend a regular user follow when deploying your Lava? For example, how should they place the amplifier, and how can they ensure the network automatically configure and work?
So in terms of deployment, I think once the initial step of deploying Lava is done, then the user interaction with the infrastructure should be minimal, if at all. So if you take a quick look at the paper, we show how this deployment how this kind of like infrastructure can be deployed, and all the design considerations, like for instance, inter-hop spacing, what amplification you need. But we foresee that once the infrastructure is in place, and there shouldn't be that much end user interaction with the infrastructure, more or less. I guess like an enterprise wireless network. So once it's deployed, then the actual user has no interaction with how it was deployed.
Thank you. And a related question is, what is the SNR range for Lava to be most effective for? As an amplifier, we both amplify signal and the noise. So I'm wondering, for Lava to be most effective, what's the best range? and how can we further increase that range?
So the way we address that issue is with, say, low gain. So that's one of the main attributes of Lava. So the reason we deploy this infrastructure is that we want to minimize a few things when we use amplification. The first one is the amplified noise. So the way we choose the amplification is such that between hops, that noise is pretty much attenuated so that we are not unnecessarily amplifying noise in the environment. Other considerations are, for instance, we don't want to have excessive interference. And that's also something that we achieve with a fine-grained distribution of the elements and the low amplification of the amplifiers. So there's a few results in the paper that show that maybe anywhere between 30 and 50 dB, given the distance that we put the hops, should be enough to make sure that there's no amplified noise, at least outside of that small space between the hops.
Thank you. And given your extensive experience, would you like to share some insights on the comparison between analog relay versus digital relay?
So I haven't had experience with digital relays. Maybe one that I've deployed in my house, probably. But I guess I don't understand like pretty much the question. So the difference between the two?
The concept is clear, but making it work and the pros and cons, yeah, I would like to hear your thoughts.
Yeah, I guess when it comes to this kind of the minimal elements that we designed, so the challenge is mostly how to arrive to a coherent infrastructure, given a small amplification, because there are several reasons to use low gain in the amplifiers. But once you've figured out the distance at which you need to place the hops, how to deploy the different elements in a suitable topology, then I think that would be the main challenge in trying to build such an infrastructure. But once you've arrived to a cohesive design, then you can simply just kind of like let it work.
Thank you. And we have a question on the Slack from Ruofen Liu. He asked how to handle the contention between different pairs of endpoints in the unlicensed band. Do you need to design MAC protocol?
So that's a good question. So the way we address this issue is in terms of like spatial separation. That's one of the reasons why we use a fine-grained topology and low gain amplification, because that allows us to kind of like separate different, spatially separate the different elements. In terms of MAC protocol, I don't think it will be necessary because the main, this is one of the assumptions in our deployment. Once you've had an established link, which is something that can be done before you even deploy the Lava infrastructure, then there's a kind of like there's a dependence on the how good the power meter is in our elements, in our different elements, to detect where the endpoints are. And so I don't foresee that MAC protocols are going to be necessary. And that's actually one of the things that we want to minimize, because we want to keep the infrastructure as generic as possible. But I guess that's something that can be explored in the future.
Thank you. In the interest of time, we are moving on, but thank you very much, everyone.
Thank you.
The second talk is on personal device. The presenter is Zhijian Yang. He's a fourth-year PhD candidate in computer science department at UIUC. He's working with Professor Romit Chandahuri. His research interest is in mobile computing, especially in wearable computing around the head and ear. Previously, he received his bachelor degree from Electronic Engineering Department at Tsinghua University. Let's play the video.
Hello everyone, my name is Zhijian, and today I'm going to present our work, Personalizing Head-Related Transfer Functions for Earables. This is a joint work with my advisor Ramit, and we are from University of Illinois at Urbana-Champaign. Imagine that you are wearing earphones and you hear a voice that says, "Hello, please come this way." Can you tell if the sound is real or virtual? With today's earphones, you easily can. But is it possible to make the virtual sound indistinguishable with the real one? Or in other words, can we fool the brain so that it cannot tell the difference? This paper aims to design a filter such that when it is applied on the original sound source signal, it can trick the brain to believe that the virtual sound from the earphone is actually the actual sound. And we call this filter head-related transfer function, or HRTF. HRTF research began as early as the 1960s. People started to use artificially created head to understand the human's head and ears effect on the sound. But up to now, HRTF design is still a challenging problem. So why is HRTF design such a challenging problem? Let's try to understand. So first, we need to understand how the sound bends or diffracts around your cheek and face. And second, we need to understand how the real signal bounces inside your ear pinna before it arrives at the eardrum. And these two aspects combined depict the HRTF at any given angle theta. If the earbud can learn your personalized HRTF, then the task of fooling your brain is actually easy. We essentially need to pass the original sound signal through the personalized HRTF filter, and then a realistic spatial audio can be created. And this can enable a lot of applications. For example, spatial audio-based navigation. Let's imagine an acoustic augmented reality scenario where the user is at the airport and trying to find her gate. We can play a follow me to your gate sound from the earphone using virtual spatial audio. And then the user can basically follow the sound and reach the destination. Of course, personalized HRTF is also very useful in VR gaming when we want to render different spatially located sound sources. Or even during virtual meetings, we can add 360-degree audio so that people can have a spatial feeling as if the other attendees in the meeting are just sitting around. However, it is extremely difficult to understand how your head and ear affect the sound. So let's look at how HRTF measurement is being performed today. Actually, it needs to be done in very controlled settings. A user is asked to sit in a large acoustic chamber and wear in-ear microphones. A large rotating speaker array can then simulate the sound effect of a sound source at any given angle. And in this way, HRTFs can be estimated. This is, of course, very difficult to obtain. So this means the spatial audio products we see on the market these days are actually using the generic HRTF. But generic HRTF is not optimal. And to understand how much suboptimal the generic HRTF is, we did our experiment. So we passed the original sound signal through two filters. The first one is the generic HRTF filter, and the second one is a personalized HRTF filter. And we ask the user to identify the sound direction in these two cases. And this direction is the ground truth sound direction. And this is the user's perceived direction using a generic HRTF. And this is the perceived direction using the personalized HRTF. And we can see that generic HRTF leads to as large as 60 degrees externalization error. So it is obviously not good enough. Then the natural question is that, can we personalize HRTF without acoustic chambers? So actually, previous researchers have used 3D scan to capture the shape of the user's head and ear. And then they will perform acoustic simulation or machine learning-based approach on the 3D scan result. And in this way, they can obtain the HRTF. This is better than acoustic chamber, but some material properties like the skin and the hair properties is still very difficult to estimate. So this paper asks, can we build a system that allows easy personalized HRTF estimation at home? And we present our system unique. Here is the basic idea for unique. We will use the smartphone as a transmitter and in-ear microphone as receiver. And HRTF is estimated by asking the user to rotate the phone around the head. And the remaining slides are organized as the following. I will first talk about unique system sketch, and then I will give intuition about two technical parts, namely the phone localization part, as well as the near to far field conversion part. And finally, I will talk about the implementation and evaluation. Then let's look at unique system sketch. We use smartphone as a transmitter, and smartphone transmits a known source signal S. And we use two in-ear microphones as receiver, and the two in-ear microphones receive signals R. We ask the user to move the phone, and IMU records motion. Then because we know the source signal S, and we also know the received signal R on both of these ears, then we can essentially estimate acoustic channel H for the left and right ear, HL and HR. And we also perform phone localization using phone IMU and in-ear microphone sensor fusion. Then if we have the precise phone location, we essentially have the near-field HRTF. Why? This is because near-field HRTF is essentially a one-to-one mapping between the phone location and the acoustic channel HL and HR. And finally, we will focus on near to far field HRTF conversion. This is because near field HRTF is not enough, because in a lot of cases, we want to create the effect for the far field sound, as shown in the grid head above in this slide where the sound source is far away. So then I will talk about the intuition of phone localization and near to far field conversion part. Let's first start with the phone localization part. So our goal is that as the user rotates the phone around the head, we want to localize each phone location at each time instance. So let's first look at a simple case. Assume we know the distance between microphones and there is no head between the microphones. Then localization is straightforward because we can essentially get the acoustic time of flight between the smartphone and the in-ear microphones. And this can translate to the distance, DIL and DIR. And then we can just perform a simple transliteration and the phone location can be estimated. But what if when there is a head in between? Then signal actually diffracts around the head instead of penetrating the head. So this means we need to model the diffractions to understand how the signal propagates. But to model the diffraction, we need head size and head shape, which we don't know for now. So what are we going to do? We propose a diffraction-aware sensor fusion algorithm. An idea is the following. So we ask the user to face the phone towards the center of the head. This means the IMU measured angle theta I can actually translate to the phone polar angle alpha I. And if we also model diffraction-based trajectorization, then we can localize the phone location as PI, and PI can also give us a polar angle alpha I measurement. And these 2 points make the system overdetermined and brings us opportunity to jointly solve for the head shape and phone location. And in this way, we can estimate where the phone is in each time instance. And there are more details in the paper about this diffraction-aware sensor fusion algorithm. And we now have the phone location estimated. By mapping the phone location with the acoustic channel, we get the near-field HRTF. And we can see that the near-field HRTF is actually coming from a point source. But in most of the cases, we will need far-field HRTF. And far-field HRTF is coming from parallel lines. And so I will talk about our next module, which is near to far-field HRTF conversion. So our goal is that we want to synthesize the far-field HRTF at angle theta using the near-field HRTF measurements that we have on the trajectory A. So our intuition is that far-field HRTF is actually a recombination of different rays for near-field HRTF at different locations. So I have plotted 3 points, x1, x2, and x3 here. So if we want to synthesize the far-field HRTF, we essentially want to pull out these parallel rays from these points, and then we combine these parallel rays together. This is essentially the far-field HRTF at angle theta. And the decomposition for the near-field HRTF is actually a very challenging problem. And I will not go into the details here, but basically we perform decomposition of the near-field HRTF and then recombine them to understand the far-field HRTF. And we now have the far-field HRTF estimated. So we pass any sound source signal that we want to render through the unique personalized HRTF filter. And in this way, we can create a realistic spatial audio for any given user. We implement unique on commercial off-the-shelf mobile devices, including a smartphone, speaker, and in-ear microphone. And we evaluate on the correlation between the estimated and ground truth HRTF. And let me first show the baseline result. This is the correlation between the generic HRTF and the ground truth HRTF. We can see that the correlation is low. And this is the result for correlation between unique estimated HRTF and the ground truth HRTF. And we can see that unique generates HRTF 1.8 times more accurate than the generic HRTF. There's also discussions about how we use our unique estimated HRTF to better understand the real-world sound in coming direction. So for more details, please read our paper, and thanks for listening.
Thank you very much for your talk. And we have time for a few questions. I will start with one. So it's interesting to see your phone localization. How do you handle multipass in the localization? And what frequency did you use? What localization error do you see?
Yeah, so thanks for the question. First about multipass. So our scenario is that we ask the user to rotate the phone very close to the head. And in this way, the room reflections that we get is actually coming from like far away. So it has a time separation. If we plot the acoustic channel in time domain, we essentially only need to focus on the very early part, because these are the passes that is coming from the phase that we're interested in, and the room reflections are very far away. So there's a time separation, and we don't need to look at the room reflections. So it will not pollute our measurements. And for the what frequency we are using, so essentially we want to estimate HRTF, and HRTF essentially compose all the frequencies, basically from 0 Hertz to 24 kilohertz in our case. So we basically use all the frequencies.
Even for localization, you use all the frequencies?
Yeah, so if we use all the frequencies, we can have a kind of more clear peak in the time domain channel impulse response.
I see. What localization algorithm did you use?
Specifically, we are using the IMU and acoustic sensor fusion, as I mentioned in the presentation. And for the acoustic part, I'm basically using the acoustic time of flight, and I'm modeling the diffraction of the head. And based on this model and the acoustic time of flight, I can estimate an acoustic base location. And also I have IMU, which gives me the orientation, and I do a sensor fusion between these two to estimate the phone location as well as the head parameters.
I see. So do you have to deal with the phase refraction, or probably it's far away, we don't need to worry, but how about phase?
Yeah, so we propose a IMU and acoustic sensor fusion algorithm, which jointly estimate the phase diffraction as well as the phone location, and there are more details in the paper about this algorithm.
Okay, cool, thank you. And I saw there's a question from the audience, Yu Tao. He asked, in the experiment, you require the user to face the phone to his head so you can translate the angle. Did you address the problem a user might not be able to do this precisely, and there are errors in these angles?
Yeah, this is a very great question, actually. So currently, our system requires the user to face the phone towards the center of the head. And I think as a future work, we can incorporate with vision. So basically, we use the front face camera of the phone. And then in this way, we can know that whether the phone is actually facing towards the face or if there is any angle offset. And then we can compensate for this angle offset.
It's nice to see the benefit you quantified at the acoustic level. Can you give some example benefit of improved HRTF accuracy for users?
Yeah, so basically, there are a lot of applications where we require the user to perceive the sound in very accurate direction. Let's say, for example, in an audio-based navigation scenario where we want to create a virtual person walking in front of the user, and the virtual person is saying "follow me," and then user can find basically destination. And in this way, if let's say the spatial audio is not coming from the correct direction, then the user may not be able to follow that virtual person walking in front of him or her and cannot find the destination. And these are the example where we need accurate HRTF.
Thank you. And Ashik Jain asked, we usually don't have accurate IMU. How does the localization error affect the HRTF experience?
Yeah, so this is a great question. So actually, we are only using the gyroscope here for the localization algorithm. We are not using accelerometer, and we know that accelerometer double integration will have big errors, and we are only relying on gyroscope one-time integration. And these days, the operating systems of the phone, they are handling the gyroscope bias pretty well. So the one-time integration on gyroscope actually gives pretty accurate this angular measurement from the IMU.
Thank you. Okay, in the interest of time, we'll move on. Thank you so much.
Yeah, thanks.
And the third paper will be on satellite networks. The presenter is Jay Shenoy. Jay is a first-year PhD student at UIUC. He works on wireless networking and signal processing. He's a recipient of NSF Graduate Research Fellowship. Now let's see the video.
Hi everyone, I'm Jay from UIUC, and today I'll be describing a novel approach for getting data down to Earth from satellites up in space. This is a joint work with Deepak and Ranveer. In the last decade alone, the number of satellites launched into orbit has increased tenfold, and this number is expected to increase by another tenfold by 2030. The majority of these satellites are LEO, or low Earth orbit satellites, and they typically fly about 600 kilometers off the ground, and it takes them about 90 minutes to orbit the Earth once. Today, 45% of these LEO satellites are Earth observation satellites. These satellites basically take pictures of the Earth from space and send the images down to the ground. And on the Earth, we have these structures called ground stations, which wirelessly receive these images. These pictures can be used for a variety of different applications, like ocean monitoring, agriculture, and disaster monitoring. For example, this picture of a wildfire can help emergency response with early detection and tracking the propagation of the fire. However, since these events are so time critical, it's essential that we get these images from the satellite in as real time and as frequently as possible. To get a better sense of how these satellites take pictures, we need to understand how they orbit the Earth. And initially, you might think that based on this animation, their orbit is perfectly circular. However, the Earth itself is rotating on its axis, and as a result, we can take a closer look and see that the satellite actually offsets with respect to its position in its previous orbit. Because of this, it takes the satellite about 5 to 6 days to actually revisit the same point on Earth. And because of this, people typically launch hundreds of LEO satellites in these large constellations so that multiple satellites can revisit the same points on Earth more frequently. As these satellites collect their image data, they need to pass over ground stations to transmit their data to Earth. And this is the challenge that we'll be tackling today. However, data downlink is definitely easier said than done. A single image of the Earth is about 500 terapixels. And even if we compress this data, a single satellite would need to send hundreds of gigabytes of data down to Earth per day. Also, the problem is that since these satellites are moving really fast with respect to the Earth, each contact over a ground station lasts only about 10 minutes. And once the satellite moves below the horizon and out of view from the ground station, it can't transmit the data to that ground station until it comes back around the Earth. As a result, we need this really high capacity downlink between a long 500-kilometer distance between Earth and space. And the way people accomplish this downlink today is that they use these large, complex ground stations that cost millions of dollars. And these ground stations have a lot of setup requirements, like buying licensing, land, and specialized hardware. Because of this, networks typically only have 4 to 5 of these massive ground stations. And this approach has a lot of shortcomings. If we look at this single satellite ground station network, we'll see these shortcomings. And when the satellite passes in this red circle, it can transmit its image data down to the ground station. But we see here that it's actually taking a while for the satellite to get to this ground station. And keep in mind, each of these orbits is about 90 minutes, like we talked about earlier. Because of this, there's a large latency incurred between image capture on a satellite and image reception on the ground. Also, scaling and trying to build more of these ground stations is capital intensive. And lastly, any sorts of failures on the satellite ground link, such as weather, can be very disruptive to the network, given that there's so few ground stations. So to address these bottlenecks, we describe a new system called low latency distributed downlink, or L2D2. And at the heart of this idea is this distributed hybrid ground station approach. What if instead of using the high complexity state-of-the-art ground stations, we instead use these cheap, low-cost ground stations that are much more simple and can be easily built with off-the-shelf components. We can also set up these ground stations in more commonplace environments like people's backyards and rooftops. And because the ground stations themselves are so simple, they can be more easily scaled and distributed geographically across the Earth. We've seen a similar sort of evolution in the networking community ourselves, as we move from these monolithic, highly centralized and expensive structures like supercomputing to these more distributed architectures like cloud data centers that use commodity computers that work together to perform the compute. And although these distributed architectures yield some important benefits in terms of reduced hardware complexity, they pose some significant challenges in terms of increased software complexity. So L2D2's design has some major benefits. First is, with more ground stations, the network becomes more fault tolerant. Any sorts of link failures in parts of the network can be more easily made up and rescheduled by scheduling links between satellites and ground stations in other parts of the network. Also, with more ground stations, the satellites themselves have more opportunities to transmit data to the Earth quicker. And this lowers our latency time between image capture and image reception at the ground. Lastly, L2D2 is a hybrid ground station approach. Not every ground station in the network needs to be transmit capable. In fact, the majority of L2D2 ground stations are receive only and spend most of their time downlinking images. This brings us to the main question of our work. Can a network of these tiny, low complexity ground stations really outperform the capital heavy solution we have today? And the answer is an astounding yes, but first we need to address some challenges with implementing L2D2's design. And the first and most intuitive one is that with so many ground stations and satellites, how do we figure out who talks to who? And today this isn't a big deal. There's so few ground stations in the network and satellites only pass over them for about 10 minutes. But in L2D2, we'll be having a lot of ground stations and an increasing number of satellites that are bound to be competing with each other for a ground station's link. In fact, in L2D2, we found that a ground station on average sees about 14 satellites at a time. And the problem is that in practice, the ground station can actually only pick one of these 14 satellites to talk to at a given instance. This makes scheduling these satellite ground links even more important. So to do this, we start by assigning weights to each satellite ground station pair and visibility of each other. And these weights are based on the link quality between the satellite and ground station. Once we assign these weights, we can also tune them to optimize for different aspects of the network, such as latency, throughput, and geographic restrictions. However, there's another aspect of this problem that makes it more challenging, and it's this idea that the ground station takes time to switch between satellite links. And this incurs some costs to the network. So now we need to optimize these links across time, and the problem becomes NP hard. So we can't explain the full details of our algorithm here, but the basic idea is we build this approximation greedy algorithm with sticky links. We start by assigning the weights like we talked about earlier, and then at time step t, we pick the optimal blue weights and ignore the orange ones. But then at time step t+1, to account for this cost of switching links, we assign a bonus factor to each of the links we picked in the previous time step. So once we figured out how to schedule these satellite ground station links, we need to figure out on optimizing the individual links as much as possible. And typically this is done with data rate adaptation. In traditional satellite ground systems, feedback or acknowledgements are used from a transmit capable ground station to the satellite so it can send data at the ideal data rate based on the link quality. But in L2D2, we have receive only ground stations that can't send these ACKs. So what we essentially need to do is predict the link qualities and the ideal data rates to send it before the satellites even pass over the ground stations. So to get a better sense of this problem, we need to understand how a satellite ground link varies over time. So here, basically, the higher the SNR, the higher the link quality and the higher the data rate that link can support. So what we see is at the beginning of this pass, as the satellite moves into view of the ground station, the SNR increases, and towards the end, as the satellite moves below the horizon and out of view of the ground station, the SNR decreases. However, toward the middle here, we would expect the SNR to be at its peak, but we see this dip in the SNR, and this is due to environmental factors degrading the link, such as multipath reflections off both the satellite and ground station environments. Lastly, we wanted to look at the same satellite ground station pass on a different day, except this day it was raining, and accordingly, we see the overall link decrease. Using the factors we just talked about, we can train a machine learning model for every satellite ground station link to predict the SNR over time and the ideal data rates to send at. So to evaluate L2D2, we start by looking at the link estimation model, and we use real-world measurements across 5 ground stations and 4 satellites in common Earth observation frequency bands. These datasets have been made public, and I encourage you to check them out at the link below. So we start by looking at accuracy of link prediction. And basically on the x-axis here, we have SNR error in dB, and on the y-axis, we have the cumulative distribution function. Here's our L2D2 model, and we compare it against a state-of-the-art model from the ITU that mathematically predicts link quality based on weather and satellite position. What we see here is that L2D2 significantly outperforms the ITU model, At the median, the ITU model performs about 2.5 dB worse in terms of SNR error. What this translates to in terms of data rate error is about a 6.25% decrease from the optimal throughput link for L2D2 at the median, but a 41% decrease from the optimal for the ITU model. And this is a really important finding. The L2D2 link estimation model can be used for a variety of other applications beyond L2D2, such as ground station planning based on where optimal predicted links would be on Earth. Also, we set up this large-scale emulation to evaluate L2D2, and we start by getting satellite and ground station position information from the SatDocs open source ground station network. In our experiments, we have each of the satellites generate about 100 gigabytes of data per day, and as they orbit the Earth, they transmit this data down to ground stations that they see. We also want to compare L2D2 to one of the state-of-the-art ground station networks. So we pick a subset of 5 ground stations and then design them to have at least 10 times higher median throughput than an L2D2 ground station. So now latency is the name of the game here. We look at latency on the x-axis in minutes, or time between data capture and data reception at the ground. And on the y-axis, we have CDF. Here's our state-of-the-art model. And at the median, the latency is about 1.5 hours. And at the 90th percentile, this latency goes up to about 5.5 hours. Whereas in L2D2, the median latency is only about 20 minutes. And at the 90th percentile, it only goes up to about 1 hour. And the reason for this is because with so many ground stations, satellites have more opportunities to transmit their data to Earth quicker. And the results of these experiments basically demonstrate that our distributed ground station architecture can reduce our latency from hours to minutes. Ultimately, L2D2 proposes this new distributed hybrid ground station architecture that can significantly reduce our latency for the real-time applications that we care about. Thank you.
Thank you so much for your nice talk. I will start with a few questions. So L2D2 has many interesting components. Which one do you think contribute to the most gain in the latency and throughput?
Yeah, so that's a really good question. And in terms of latency, the biggest one is probably the idea of geographic distribution. And the losses in latency that we see today due to like the state-of-the-art ground station networks is that there's so few ground stations and they're not very consistently spread throughout the Earth. So as a result, the satellite is actually spending most of its orbit just holding its data and not transmitting anything to the ground. But in L2D2, since our ground stations have much lower complexity, they can be scaled out more easily and spread out across the world. And this basically gives satellites more opportunities to transmit their data down to Earth. And the sooner that the satellites are able to transmit their data down, this significantly reduces latency. And in terms of throughput, also, I'd say the same sort of benefit of having geographic distribution and just more opportunities to send data down is another big factor, because any sorts of faults or like failures in certain parts of the network, like bad weather degrading the link in that area of the transmission, they can be more easily made up by scheduling links in other parts of the network.
Thank you, interesting. And second question is the variation is done using the data from large existing satellites. What do you think as we move towards many more low-cost stations, would it affect range and link quality and overall, what do you think might be changed?
Yeah, yeah, that's also a very good question. So I think basically these like smaller ground stations just achieve lower data rates. That's like sort of the biggest downside of them. But in terms of functionality, they sort of rotate to track the satellite in the same way, and managing position like properly is a big factor affecting the link quality. In either case, with even like low cost ground stations or big ground stations, weather plays a large role in degrading the link quality. And I would say that remains consistent overall as well. And the last main factor that we found that contributes to like the link quality variation is this idea of multipath sort of reflecting off both like the ground station and the satellite environments themselves. And that's pretty variable, either in the state-of-the-art ground station network or a low-cost ground station network. So I would say like the biggest downside of the lower cost ground stations is the amount of the data rates we can essentially send through the link.
Cool. I saw lots of questions coming in from the audience. From Wenjing Yan, he commented that L2D2 scheduling optimization goal mainly are downlink throughput and latency. Would this mechanism affect the satellite energy consumption as well as satellite on-service lifetime from the long-term aspect?
Yeah, so that's a really good point made. So yeah, if these satellites are like today's satellites don't spend as much time transmitting data to the ground since there's so few ground stations. But in L2D2 with so many more ground stations, satellites need to do a better job of basically managing their power budget since they're going to be constantly transmitting data to the ground. And to be honest, this is like an open question that we sort of addressed in the paper, but is not something that we fully looked at. But different techniques on sort of managing like solar panels on a satellite and figuring out how to better harness and store energy on satellites is a very good direction for future work.
Cool. And from Vijay Shah, he asked, what are the distributed Earth station? Who owns it? How many did you assume for experimentation? Any distribution for it? Is there any data set available?
Yeah, that's a really good question as well. So basically, we use actual ground station locations, and we got the distribution or the positions for each of these ground stations from a database called SatNogs. And so these are actual ground stations that people have set up, and we chose a subset of about 200 of the most popular used ground stations for our evaluation. And we weren't fully able to control this distribution since these are already pre-existing ground station locations. But we felt that using this made the evaluation more realistic in the sense that these are actual spots where our ground stations could possibly be set up.
Cool. And from Wenjing Yan, it seems that L2D2 systems needs a good synchronization for practical deployment. How does the general internet delay affect the real-time performance of L2D2?
Yeah, that's a good question. So the biggest thing is sort of this idea of sending acknowledgements between a receive-only ground station and a transmit-only ground station. And since the size of these acknowledgements are just bitmaps and they're really small, the delay through the internet, we don't find it to be that long. And given the amount of time between a satellite's transmitting data over a receive-only ground station and its orbit over one of the ACK-capable ground stations, we would find that the bottleneck is probably the satellite's orbit rather than the delay through the internet.
Cool. And from Deborah, can your matching algorithm take into account complex policy? For example, some application may not want their data to be routed through certain locations. Yeah,
that's a really good question. So this is sort of goes back to the scheduling algorithm I talked about in the presentation. We basically have this, this value function implemented in the scheduling algorithm, and it can tune each of the different weights between each of the satellite ground links. And you can account for these different issues such as prioritizing or like figuring out which ground stations should be restricted and which ones you actually want data to get transmitted to.
Thank you so much. And I will invite everyone to continue the discussion on the Slack channel. And in the interest of time, we'll move on. Thank you.
Thanks, Lily.
The final paper is on vehicular communication. The presenter is John Noren. John is a third-year PhD student at UCSD working on passive smart surface. He's also a senior RF engineer at Cubic, a San Diego-based company, and has worked there for 5.5 years. Let's watch the video.
Hello, my name is John Nolan and I am a PhD student at UC San Diego. I will be discussing our work on ROS, a passive smart surface for roadside to vehicle communication. Intelligent transportation systems would coordinate motorists, pedestrians, and public transportation by exchanging information between them. They have the potential to reduce traffic accidents and deaths, optimize transportation resources, and even relieve humans of driving through the use of autonomous vehicles and interconnected transportation systems. Due to the complexity of these systems, however, these technologies require significant amounts of information about the static and dynamic surroundings, such as traffic lights and signs and common roadway rules. The current trend in research focuses on smartening the vehicle as much as possible. This trend places the entire burden of realizing an intelligent transportation future on the vehicle itself. These intelligent vehicles use a multitude of sensors and technologies such as V2X, DSRC, 5G, Wi-Fi, LiDAR, and many others. For example, a Tesla vehicle today uses 8 cameras, sonar, GPS, radar, and a custom neural net computer system to achieve its current state of autonomy. This current trend pushes non-intelligent vehicles out of the ability to be somewhat autonomous and increases the cost of deploying autonomous vehicles altogether. Therefore, it is critical that intelligent infrastructure supplement intelligent vehicles. This will reduce vehicle sensor requirements, thereby also reducing the overall cost and complexity of these vehicles. Unfortunately, there's one major problem. Our current infrastructure isn't very smart. Aside for complex traffic light networks in large metropolitan areas, roadway infrastructure consists entirely of visible road signs. Visible road signage requires the full attention of the driver and does not lend well for roadway optimization. To one day achieve intelligent transportation systems, the visible road sign will need to be updated. Current solutions try to process road sign information by using extensive camera systems paired with complex computer algorithms. These solutions, however, aren't optimal in all driving scenarios and are currently mainly used as aids to assist motorists in making decisions instead of completing the task for them. Other solutions set out to create detailed maps and databases of all the driving locations and road signs to obtain vehicle autonomy. One easy solution to circumvent these issues would be to implement vehicle to infrastructure communications, such as dedicated short-range communications or RFID, for example. These solutions, however, would complicate either the road sign, the vehicle, or both by requiring the installation of dedicated hardware. Overall, system complexity and cost will not be reduced. This is where ROS can help smarten current road signs without modifying existing vehicle hardware. ROS is a passive millimeter wave tag that can encode information in its geometrical layout. Current millimeter wave automotive radars can sense and read the information encoded within ROS as it drives by. Similar to how road signs are retroreflective to visible light, meaning light is reflected back in the direction of the source, ROS is retroreflective to millimeter wave radar signals. ROS is fully passive and chipless, and because of its planar construction, can be easily integrated onto current road sign infrastructure. For the ROS tag to be useful and reliable, it must satisfy a few requirements. ROS must operate at long distances and be easily detectable by automotive millimeter wave radars. ROS must perform well in many driving conditions and in many driving scenarios. And in addition, the tag should encode sufficient amounts of data to accommodate the many types of road signs today. So with that, radar communications are governed by the radar range equation. Passive millimeter wave radar links pose unique challenges to the system design, unlike their active lower frequency counterparts. To achieve long-range radar communication at millimeter wave frequencies, it is important to optimize the radar cross-section of the device. In addition, a retroreflection is paramount for long-range visibility at many viewing angles. To address this challenge, ROS utilizes Venata arrays, which are pairs of antenna elements connected by transmission lines with predefined lengths. Venata arrays are inherently retrodirective due to the phase conjugation that occurs to the incident millimeter wave signals as they propagate through the array. ROS uses Venata arrays as building blocks to create stacks of arrays, which allows for the scalable increase in radar visibility and range. The ROS stack uses aperture-coupled patch antennas to realize the Venata array retroreflective concept. Aperture patch antennas were selected so that the transmission lines could be placed on separate layers using strip line transmission lines. Strip lines are advantageous because they are shrouded by ground planes both above and below the transmission line, which reduces spurious radiation as signals propagate through the transmission lines. The aperture-coupled patch antenna was optimized by adjusting the length and width dimensions of the patch, along with the H-slot opening parameters. The optimization was concluded when the return loss was less than 10 dB across the millimeter wave radar band. The ROS stack-up consists of 4 copper layers using 2 Rogers 4350B cores bound together by Rogers 4350F prepreg. The top layer contains the patch antennas, followed by the H-shaped aperture ground plane. Below the antenna ground plane lies the strip line layer, followed by the second and final ground plane. 6 aperture-coupled patch antennas are connected by strip line transmission lines to form a single Venata array. These arrays are then placed linearly in a vertical fashion to create the ROS Venata array stack. The stacking of these arrays, however, creates an unwanted effect of very narrow elevation beam widths in the radar cross-section of the tag. Narrow beam widths can create problems with antenna misalignment between the vehicle's radar and the tag, reducing detection accuracy and range. To circumvent this issue, ROS shapes the elevation pattern of the Venata array stack by increasing the length of the interconnecting transmission lines to encode predetermined phase weights onto each Venata array element within the stack. As phase weights are applied to each array, the relative positions of the arrays within the stack change and are dependent on the phases applied to all the other elements. Therefore, a differential genetic evolution algorithm was used to search the solution space to arrive at a set of weights that satisfied the elevation pattern criteria. By shaping the elevation radar cross-sectional pattern, antenna misalignments can be avoided. A third challenge is ROS must be able to perform adequately in heavy multipath environments. Environmental interferences from surrounding objects such as other vehicles, buildings, pedestrians, etc., could potentially overwhelm ROS's return signal, burying it within noise. To mitigate this challenge, a polarization switching Venata array is used as the fundamental building block within a Venata array stack. The polarization of the return signal is rotated to an orthogonal polarization. The surrounding objects, however, tend to reflect millimeter wave signals with roughly the same polarization. By switching the polarization, the radar can then discriminate between the ROS tag and the surrounding object's reflections. Lastly, ROS should allow for large encoding capabilities. Some common data encoding techniques modulate the timing of pulses reflected back to an interrogator using reflectors spaced out at predefined distances. Another technique is to encode information in the frequency response of the return signal by attenuating select frequencies using notch filters. Both of these techniques can create unique RF signatures within the return signal, but at millimeter wave frequencies, however, these techniques are not easily realizable. Therefore, ROS encodes information spatially using polarization switching Venata array stacks as bits. Each stack can be modeled as an omnidirectional radar cross-sectional pattern. The tag, which consists of a collection of these stacks, will have a superimposed RCS pattern of all the stacks within it. The resultant superimposed pattern will have encoded within it as well the relative spacing of all pairwise stacks. The vehicle passing by the tag captures the radar cross-sectional pattern and performs a fast Fourier transform on the data to decode the underlying relative distances, or in other words, the geometrical layout of the tag. Using a commercial off-the-shelf TI radar mounted onto a sedan, measurements were conducted to verify the performance of the ROS tags using polarization switching Venata arrays. The TI radar is used to localize objects in the environment. The radar data is then used to generate a point cloud of the surrounding objects with a strong RCS. From the point cloud, the relative location of the object to the radar can be determined and an RCS plot can be generated. The encoded data from the ROS tag can then be extracted by performing an FFT on the collected RCS data. The ROS tags consisting of 32 element stacks can consistently achieve signal-to-noise ratios of over 14 dB out to 6 meters. This signal-to-noise ratio corresponds to a bit error rate of 0.6% using the on-off keying modulation model. Higher signal-to-noise ratios can be achieved using smaller number of elements but at reduced ranges. ROS tags are resilient to elevation misalignment due to the elevation beam shaping pattern, maintaining signal-to-noise ratios of 15 dB or higher. Lastly, ROS tags have been experimentally verified up to 30 miles per hour and can maintain bit error rates smaller than 0.6%. To conclude, ROS is a passive chipless tag that is retroreflective to millimeter wave signals and acts as a barcode for roadsigns. ROS encodes information within the monostatic radar cross-sectional pattern of the tag. Current millimeter wave automotive radars can sense and read from ROS and can achieve bit error rates greater than 0.6% at 6 meters. Thank you for listening.
Thank you so much for your nice talk and interesting work. And I'm interested in learning what do you think about further improving the range? Currently, you show the 6 meter range for vehicular. Certainly, sometimes we need a higher range. What avenue would you recommend other researchers need to look into to further improve the range?
Yeah, so to increase the range, the main difficulty was the near field to far field requirement. So to increase the RCS, you have to make these tags much larger, but then that further pushes the near field requirement. So one avenue would be near field focusing antennas. So if you can design these near field antennas to focus energy in a certain range of distances, you could achieve much larger ranges with more, with higher ranges and SNR.
I see. And would you also like to share your insight for the choice of the frequency 77 to 81 gigahertz?
Yeah, so we wanted to use equipment that's already available on cars today. So, you know, you can go purchase a car with automotive radars at these frequencies. And because, you know, this area is, I guess, growing, it's nice to be able to make a design that can work with cars. So, you know, these development kits are directly from manufacturers that work with other car manufacturers. So these tags can work with cars today.
Cool. And you mentioned that your scheme can support 30 miles per hour. Do you see the impact of Doppler at that speed? What would you expect when you want to push the speed?
Yeah, so in the paper, we mentioned that the actual maximum rate that we can achieve is around 80 something miles per hour, 86 or something like that. We only verified up to 30 miles per hour because it got quite difficult to find a space to do that testing. But technically, the limits there are the radar. So the development kit that we had only supported certain frame rates. So with slightly better hardware, we can achieve much higher speeds if necessary.
In terms of algorithm, do you need to worry about Doppler?
No, so Doppler is pretty insignificant compared to the frequencies that we're measuring. So these are much, much smaller.
I see. Good. And yeah, we have a few questions coming in from Joe Old. He's curious about, do you assume all? Okay, sorry, that's for the previous talk. For the latest one, how does iOS extend to multi-tag, multi-radar setup? Is there any fundamental limit on how many of these devices?
So with a multi-tag setup, actually, we briefly mentioned in the paper that that's one way to encode more information. So if you align tags spaced at certain distances, you could technically encode more data. The only requirement is you have to be able to separate the tags based off the 3dB beam width of your radar. So certain radars only have a certain number of antennas. So the more antennas you have, the sharper the 3dB beam width, so you could encode more tags. Now with multi-radar, in our paper, we also discuss having 2 radars. And the nice thing about that is all these different radars are technically not synchronous, so their phases won't align. That's one benefit. And the other benefit is that these ROS tags are retrodirective. So essentially they form a beam passively at the radar that's talking to it. So other radars, their contributions are much weaker. So depending on the size of the tag that you create, that beam is more narrow and sharper and has higher SNR. So the other radars are basically within the noise. They're like 10 dB down depending on the size of the ROS tag that you make.
You see if there's a fundamental limit on how many of these devices can support?
So the fundamental limit would essentially be how much space physically you would want. So if you have a 3dB beam width that requires these tags to be separated by a meter, you probably don't want to have 10 of these aligned, because that would require 10 meters of roadway. So it all depends on the system architecture. How good is the radar? What is the beam width of the radar? And then how much space is available. So in our experiments, we did 2. So we had 2 tags and 2 radars, and they were spaced, I believe, half a meter or so.
Cool. Yeah, I will invite others to continue discussion on the Slack channel. Thank all the speakers for the excellent presentation, and thank audience for attending and the great questions. We will have a short break at 3:50 p.m. Eastern Time. We'll have session 4 on programmable data plane chaired by Professor Mohammed. And see you then. Thank you.